Hi, I'm Igor. In this tutorial we are building Posner Cueing Task. So let's get started. Okay, we have our Visual Studio Code running. We are in a Posner folder. So we are building a Posner Cueing Task here. And this is the recreation of the tutorial done earlier this year by John and Becca for PsychoPy. So let's see how to do this in pyFlies. Start as usual by creating a PF file, so we'll call it posner.pf. So it will be pyFlies file. And let's start with typing test, pressing tab, and then calling this test Posner. Okay. So in this experiment we have a Q shown to the subject. The Q is an arrow pointing left or right, and it's located at the center of the screen. And then we have a target that is displayed either on the left side of the screen or the right side of the screen. So if the Q is pointing to the place where target will appear, we say that trial is valid or congruent, and we say it's invalid or incongruent otherwise. So our condition table will have a variable called Q direction. So it will be the direction of that pointing arrow, and then we will have the place where target will appear. So we have target position, and I will just add another variable called isValid, which will be a Boolean variable that will hold the value of true or false, whether it is valid or invalid. So the Q direction, if you recall from getting started, we could just type here the exact values. For example, Q direction could be left, and the target position could be left, and it will be valid. And then Q direction could be left, the target position could be right. Right, and it will be invalid, and so on. So you can specify your condition table as usual by providing all the values. In pyFlies we usually do this by providing expressions and letting the table expand automatically during compilation. In this case, our Q direction will be left, right, and then we will say loop. So this little expression here is a list. It's the same syntax like you would do in, for example, Python or some other languages. And we say loop, which is applied to that list. That means loop over this list and provide row for each of its values. Notice that we are using abstract term, left and right. Those are not strings, we call that symbols. And in pyFlies we usually try to avoid being too specific. If we say that Q direction is pointing left or right, we just use words left and right. And the target position will also be left, right, and we'll say loop because we want all the possible combination left and target left, and left Q direction and target right, and so on. So we have two loops. The loops in these condition tables are evaluated from left to right. So the left loop will be the outer loop, and this right loop will be the inner loop. And here isValid will not be constant anymore. It will depend on the current values of Q direction and target position. So we can specify that by providing a Boolean expression. So isValid is when Q direction is equal to target position. Okay. So that is nice, but we can do even better because we can see here left and right is repeating. So we'll just cut this out and go here and specify variable called directions, which will be left, right, and I can use that variable here, directions loop, and then target position will also be directions loop. Okay. Notice another thing here. We are abstracting away Q directions and target position. We are using a left and right for both Q direction and the target position, which are actually different things, but they are represented here with the same words, left and right. Okay, now let's start with our components in each trial. Here we won't use any fixation, so I'll just delete this fixed part. And for execution part, we will have the same thing that happens in each trial, so the execution part will be just exec and nothing more. So this expression here won't be any more complex than this. And on the right side, we will have our components that will be displayed to the subject. First, we need to display an image of a Q that will point either left or right. And this is probably the best place to just go and shamelessly steal this Posner zip from John. So I have it here, and this Posner zip contains images, these nice PNGs. I will just take this images folder and put it here right beside my Posner.pf file and go back. These images represent the Q, so the arrow pointing left or right, and here is the target. Okay, so now let's see how we can show the Q. The component for showing images in pyFlies is called image. So just start typing EM and you already get this handy snippet. Just press tab and the snippet is expanded, and you can see that there is a parameter called file, and it expects relative path for the image. So relative path meaning relative to our experiment file. So it will be just images, and we are using / to separate path, and then the Q is called arrow underscore left and arrow underscore right. So the fixed part of the image name is arrow underscore, and then we have this variable part left and right, and it is nicely aligned with our Q direction symbol. So we'll just say Q direction, and this will be interpolated as a part of the name based on the current trial, and we'll just continue with .png. So this little image specification will show images, and we can say for how long. In John's and Becca's tutorial, I think they are using 700 milliseconds, so we can say, for example, 700. But let's make it more interesting. Let's say we want this duration to be random from 500 to 900. So this is the range expression, 500 to 900. And it is a shorthand for a list of numbers in this range. But I will use now choose operation over that range. And this choose will randomly pick any element of a list or any element of this range. Okay, let's now specify our target appearance. So the target will also be image. I'll just say image. And then the relative path will be images / now we have a constant name, so this is just target.png. And the duration, here we want this target image to be shown in indefinite duration until the subject click mouse on this target. So we won't do here we won't specify any duration. Okay. The third thing to do is to say mouse. So mouse accept the target parameter. If it's not given, then any click is valid. And we want here only click on a target to be valid. So this target will accept the name of the component or the list of valid components. In this case, we want only the target image to be valid. I will call this target target, and we need to provide this name to this component, because if we don't, there will get some generic names. The way to name a component is to type its name just before its type and separate by colon. So now this component is called target, and this target parameter will have a value of target, so it will be connected to this. Okay. Let's now finish by creating a little screen. Intro, welcome. Let's say thanks for participating in this experiment, and so on and so forth. And then we provide a flow of the experiment. Flow defines the sequence of execution of each test and each screen. In this very simple experiment, we will just have introduction and then execution of Posner. Okay, that's more or less it. Now, if you recall getting started, we'll now do some code generation. I will just start the terminal session, and you know that I will have to install Python virtual environment. I will just do that quickly here. If you don't know how it's done, go to the getting started tutorial. So now I have virtual environment, and I will just quickly say here that I want system level packages, just not to forget that. And then I will source virtual environment, and then I will pip install psychopy, and it will pull everything needed. Okay, so we are all set. I will just rehash here because I'm using Z shell interpreter, and it will just invalidate the code completion cache. First, we will start by generating a CSV file. Generate, our input will be Posner. I will overwrite, and the target will be CSV. And here we have our CSV. So it's very simple, just 4 rows. And we can see here that we could actually improve this task, because in Posner we should have more valid trials than invalid trials in order for a subject to gain confidence in a queue and for a Posner queuing effect to be observed. Let's change this condition table a little bit. Let's first go with the separation of valid and invalid trial. So our valid trial will be when we loop over a queue, and then our target will be just the same. And now we can here use constant expression true. So this will be our 2 valid trials, and our invalid trials will be looping over same direction. And here we need the opposite of queue. In order to do that, I will use if expression. So I will say it will be left if queue direction is equal right, else it will be right. And is valid will be here false. Okay. Now we have separated our valid from invalid trial, and now we need to increase the number of these valid trials. For that, I will just I'll just go by right clicking and say insert column to the left. Okay. And I will call this variable ordinal ord, and now I will use looping here to increase the number of valid trials. I will loop from 1 to 4, and for this here invalid, I just need 2 invalid trials. So I won't loop, I will just say 5, because this will expand from 1 to 4, and for each ordinal we'll have 2 directions, right? So it will be 4 times 2, 8 in total, and here we will have 2 where ordinal will be 5. Okay, nice. Let's regenerate our CSV. let's go to CSV. Now we have 10 rows where we have 8 valid trials and 2 invalid trials. Okay, next thing to do is to generate log to investigate our experiment in greater details. It provides us with a lot of information with all the components and the default values of their parameters. And here we have flow, and we can fold everything and then unfold what we are interested in. For example, this screen will have this content, and this test will be with this table, and there will be some trials, and I can pick any trial. For that trial we will have this variable in our condition table, and total variable will be this, and there will be execute phase with these 3 components, and I can observe an error here. I can see that the target image is displayed at exactly 0 milliseconds, the same as the Q image. We won't do that, right? We actually want for a target image to appear when the Q image is over. So let's fix that. In order to specify when the component is going to appear, we use at keyword, and then we use time reference expression, where the most simple time reference expression is just an absolute value. So for example, at 400, meaning at exactly 400 milliseconds. For example, if we specified here a constant value, we could use here that constant value and it will be fine. But since we put here a random value, we cannot use absolute value here. So we will use a relative value, and relative values are given by specifying plus or minus and then the number. For example, if I say plus 200, that means 200 milliseconds after the previous component finish. And if I want to say 200 milliseconds after the previous component start, I will just add a dot that will anchor this expression to the start of the previous component. So if I want relative to the start, I use dot. If I want relative to the end, I just specify without dot, but I specify plus. And here we want this target to appear exactly when this queue finish. So I will just say at +0. And let's now regenerate our log file to see if we are now better here. Yes, we are. We have now 758 milliseconds for this trial, where the duration is exactly 758 milliseconds. And the mouse component will start at the same time, and that's correct because we want our mouse to track the time from the onset of the target. Okay, let's now try to run our experiment. So we have our flow, everything is set. Let's generate PsychoPy, and let's start it. So we start Posner. Okay, the dialog, and we should have a welcome message, and when I press space, we have our queue and our target, but we can observe another error in our experiment. Our target is displayed at the center of the screen, which is not what we wanted. So let's terminate our experiment with escape. Go to the model, and we can see that for this image, we don't provide position, and by default, it will be center of the screen. If we go to the log, we can see the same here. So in order to fix that, we will specify here the position, and the position will be target pos. So that's the position of the target. Let's now regenerate our PsychoPy code and rerun. Okay. And our experiment is over. So we have another problem. If you observe it carefully, you will see that we have exactly 8 valid trials at the beginning and then 2 invalid trials. Of course, we don't want that. We actually want our trials to be randomized. In order to do that, we can call our Posner test with parameter random set to true. You can pass in parameters to screens and tests, and it's a powerful way to customize them or to alter their execution. And 2 parameters are special. One is random. If set to true, then the trials will be randomized. And the other is practice. If set to true, then no data will be collected during that execution. So let's now regenerate again our CyclePy script and run it. Okay, now let's see if we have okay, I'm a little bit flaky, so I'm not sure whether Posner Cueing effect will be observed in this experiment run. Let's now see, we have this data folder created. It's created by CyclePy, and if we go to the data, we can see here that we have some data collected, and we will have all the values. So each row will be one trial, and we'll have all the values of all the variables, and there we will have all the very interesting properties of each component. And here we are interested in this is valid, and we will sort by that. Let's quickly sort to separate valid from invalid. And then I will just quickly hide all these columns, and then I will insert here new column to quickly calculate the average of these invalid trials, and then I will quickly calculate average of this valid. And as you can see, there is a large margin, so the Posner Cueing is observed. We need more time to respond to these invalid trials than to these valid trials. So that's the Posner Cueing effect. Okay. So that's it for this tutorial. I hope that you find this interesting, and I hope that you will enjoy using pyFlies. So if you are interested in pyFlies, the next thing you could do is to go to the pyFlies GitHub account. You can go to the documentation, and here is the link to GitHub, where we have an organization where we have currently 3 projects. This is the language itself, this is the extension for Visual Studio Code, and this is CyclePy compiler. If you go to the main project, you can find some examples, and you can ask questions or propose changes in the issue tracker. So this is an open source project, and I do encourage you to register issues if you have any problem or if you have any ideas to propose changes. So that's everything for this tutorial. Thanks for watching, and I'll see you in the next video.